All right, ladies and gentlemen, we're going to do some calorimeter equations. We're going to actually do a practice problem out of this book right here. Book I'm working with my class, Exploring Creation with Chemistry. This is Apologia curriculum, high school course, and we're going to use the extra practice problem number 7, which you can find in at page 570 in the book if you're interested. This is just something that is very typical of many of the questions that are probably the hardest questions in Module 2. So let me just point us toward the whiteboard here. Very fancy whiteboard. Right now it looks simple, doesn't it? There's not much to look at, and it feels so good, right? But I'm going to add your stress level up a little bit. Add to your stress. There it is. There's the equation number 7. Got it written out there. And wow, how's the stress feel right now? Stress goes up, right? Because, at least it does for me, because there's a lot of words here, a lot to manage, a lot that we could get wrong, a lot of potential pitfalls here as we go through here. So I'm going to show you a way to stay organized while we do this. But first of all, I want to show you what I always do when I get a practice problem like this. I always go to the end of the problem, because why I want to know what the bottom line question is. The bottom line question of this big question is right at the end. It's usually at the end. We can always go to the bottom. Forget about reading it. That's just going to be blah, blah, blah. But let's go to the end. What is the C of the metal? That's the question. That's what we got to find out today. What is the C of the metal? And if you're not quite clear on what C is, we'll talk about that in a little bit. What is the C of the metal? So let's just put that up here so we always know what we're looking for. What is the C of the metal? In chemistry, we always have to know what we're looking for. I'm going to even circle that so we make sure the end of our tunnel here is to find out what the C of the metal is. That's our objective. Now, the side note here, if you plan on going into politics, this would not be a good skill. In politics, we would probably want to try to see how we could avoid the question, right? So, because obviously you might lose some very important votes if you answer a question directly. So we want to learn how to avoid questions in politics. But in chemistry, it's a little different. We actually want to find out the answer to a very specific question. Okay, so let's get this out of the way. Too much information. Get out of the way. We'll get back to you in a little bit, and we're going to create a little graph here to keep organized. I need to stay organized, otherwise I lose track of where I am, and then I just gives me a big headache, or I start getting wrong answers, and that's no fun. So let's just stay organized here. What I do to stay organized is I make myself a little table, and on that table I have 3 columns. I have one column for the object. Object is typically metal, at least it has been so far in our questions, some kind of metal. The next thing that we have here is the liquid, and typically the liquid is water. Water is very easy to use for calorimeters, but it isn't always, as you might have noticed already in your questions. So the liquid, and then we have all the variables for a calorimeter. I'm just going to put cal meter. Okay, so all those variables go right here. Okay, what variables are we talking on here? On the side, I've got all our variables listed out that we like to find when we're dealing with calorimeters. Not only do I have the variables, M, C, T of F, T of I, delta T, which is change of temperature, and Q, I have the units we typically use for these. We don't have to use these units, but these are the ones that we're going to use most often, and they're easy to use. It's very important we stay with the same variables, the same units. If we notice a different unit, we're going to have to convert to keep the units the same. Otherwise, obviously, we're going to get the wrong answer. So, what we're going to put here is mass, that we use M for mass, C for specific heat, and remember the end of our tunnel is the specific heat of metal. This is the metal, so this is the end of our journey right here. I'll circle that so we keep track of that. Then we have the T, I put over here on the right, T of F, final temperature, T of I, initial temperature, and then delta T. I put those here just so that I can keep track of what it takes to get change of temperature. These two are necessary for change of temperature. Last item on my little table, the thing that I want to get a hold of is Q. Q is the heat or heat energy. Okay, all those I have listed out, and we'll refer to that. Okay, so should we get the problem back out? Let's get the problem back out, but we'll throw in a little what I like to call a stress reducer. This is my stress reducer here. Okay, this is too much information, so let's just start from the top. Let's keep it simple, one line at a time. All right, feel the stress go down? We're just focusing on the top line. A 250.0, remember it's important to keep all the digits, 250.0 gram mass of metal. Okay, stop there. Metal, object is metal, 250.0. Well, let's use a different color. Pardon me, but I just want to use a different color. Stick of blue. Let's go on to green. And let's put, what was it? 250.0 grams of metal. We don't know what kind of metal. That's all we know. Okay, so we plug that in. Okay, going on to line 2. At 112.4 degrees Celsius. So the starting temperature, the initial temperature, right here, 112.4 degrees Celsius. Okay, it's the initial temperature. Back to our equation. Okay, stress reducer is up. It is dropped. 112, the mass of metal started at that temperature, was dropped in a calorimeter. And this is the information for the calorimeter. Okay, so we got two pieces of information that are important to us. We've got a 1.40 joules over grams times Celsius. Those are the units we use for specific heat. So the specific heat C is 1.40. You can always go back. So specific heat's on this column. 1.40 joules over grams times degrees Celsius. Okay, that's going to be the unit for all of these. Grams is going to be unit for all of these. We got to make sure that is true. Okay, so what else on this line? The calorimeter has a mass of 5.0 grams. Okay, don't say 5, 5.0. That's what they gave us because that's going to be important information. 5.0 grams on the calorimeter. Okay, what else? Plugging away. Now, this mass of metal that's dropped in the calorimeter is going to contain 150 grams of water. 150.0 grams of water. Okay, let's throw that in. The liquid is water, and it's going to be 150.0 grams of water. What else? It's important to remember that that's water because that's going to help us in a little bit. Then the next step, the water and calorimeter are initially at 25 degrees Celsius. And that's true for all calorimeters. They start, the liquid and the calorimeter start and end at the same temperature. They start at the same temperature, and then the final temperature ends up being the same among the two. So they started at 25 degrees Celsius. So I'm going to put 25. Is it 0.0? No, just 25 degrees Celsius. And they ended at, so I'll just put 25 degrees Celsius. No point. 25 degrees Celsius. And let's go back to our equation. We're working our way down. The metal was dropped into the calorimeter. That was the information. It had this much water. The water and the calorimeter started at 25 degrees Celsius. At the end of the experiment, the temperature of the water, calorimeter, and metal, and that's true in all calorimeters, we wait till all the temperature of everything, including the metal, arrives at the same temperature. We let it stabilize. And in this case, it stabilized at 37.0 degrees Celsius. 37.0 degrees Celsius. 37.0 degrees Celsius. And the metal, 37.0 degrees Celsius. So, basic concept of a calorimeter is we put hot object in a room temperature, typically calorimeter. 25 degrees is typically room temperature. The heat dissipates, the heat is reduced to a final temperature of 37, and on the calorimeter the heat is increased to a final temperature of 37. It stabilizes out, and now we can start figuring in our change of temperature. I'm going to take a quick look to make sure my information was correct. And no, it wasn't. Glad I caught that. When I wrote down the question, I wrote 25 degrees Celsius, and I looked at the question there. It was actually 25.0 degrees Celsius. So it's good I double checked. Check your source. 0.0 degrees Celsius. 0.0 degrees Celsius. All right. Okay, so do I got everything I need? Yeah, we pretty much got every piece of information. We ended with 37 degrees Celsius. What is the C of the metal? Reminds us what our ultimate objective is. Now we can throw this away, cast it away. We don't care about you anymore. We've gotten everything out of it that we need to, and we can start looking at some equations. The first equation that's going to really help us, that we should have memorized for the test, is that the C, or the specific heat of water, is 4.184 joules over grams times Celsius. It's always joules over, in our case, joules over grams times Celsius, degrees Celsius. But what is it? What's the number going to be for water? Since we know it's water, it's 4.184. Okay. Is this starting to get a little cluttered? Let's put some boundaries here and keep us from getting too cluttered. How about that? Does that help? It's helping me. Okay, so we've got the specific heat of water. This is our objective. We don't know what that is yet. Don't know what kind of metal it is. So what do we do next? We need to find out the change in temperature all the way around. Well, it's an easy equation. It's kind of intuitive if you think about it. The change of temperature is the final temperature minus the initial temperature. Final temperature minus the initial temperature. These are always going to be the same. If they give you the information for the liquid, it's going to be the same for the calorimeter. You can calculate it out, plug it in over here, and you're going to have the same change of temperature. That's always true. That's how they work. But in this case, they gave it for both of us. So we can be very confident that that is true. So what we're going to do is final TF, 37 for these two. Initial TI, 25. The difference being pretty easy. 12.0 degrees Celsius. Okay, I'm being slow and careful because I want to know that I'm using the same amount of precision as the least precise measurement. They're both the same precision. They use tenths. So I'm going to use tenths in my answer. Okay, guess what? Liquid, same change in temperature. Easy. Plug it in. Look at that. We're filling this thing up. What is this one? Now this is going to be a little weird because we're going to actually get into a negative. And that makes sense because it's releasing temperature. So if it releases temperature from 112 to 37, you're going to obviously get a negative temperature. In other words, the temperature is going to drop when you put a hot piece of metal in the calorimeter. So let me get my calculator out here. I'm going to put 37 minus 112.4 equals. Okay, so 37 is the same as 37.0. I put that in. We get a minus 75.4. A minus 75. Should we use 0.4? Yeah, because the question uses tenths. So we're going to stay with tenths and keep it that way for our answer.